Jai Hind, myself Neha Garg. I am assistant professor in Ajay Kumar Garg Engineering College, and the topic is the PN junction diode. This topic has been taken from the subject BEC 201, that is the fundamentals of electronics engineering. So the topic is the PN junction diode. So diode is a two-terminal device, and it conducts a current in only one direction. And if the diode is forward bias and it is idle diode, then it will considered as a short circuit. And if it is reverse bias, then it considered as an open circuit. So PN junction diode. So we can understand this PN junction diode in three modes. First is the zero bias condition, and second one is the forward bias, and third one is the reverse bias. So in zero bias condition, if we connect the p-type semiconductor with the n-type semiconductor, so in p-type semiconductor we can see there will be holes, electrons, and acceptor ions are there. And in n-type semiconductor, electrons, holes, and donor ions are there. So if we combine the p-type semiconductor with the n-type semiconductor, then due to the diffusion process and the concentration difference on both type of charge carriers, holes from the p-type semiconductor, they will migrate towards the n side, and electrons from the n-type semiconductor, they will migrate towards the p side. And at the junction, these holes and electrons, they will get recombined and will get disappear, and at the junction point only these acceptor ions and donor ions will be there. They are immobile in nature, they cannot move within the semiconductor material. So this region is called the depletion region, and means the depletion region is that region which is deployed of the free charge carriers, and it is also called the space charge region. So this and the potential that is developed across this depletion region, that is called the barrier potential. It stops the further movement of the majority charge carrier, and due to which in zero bias case the net current will be zero. So this is how we can connect the diode in the forward bias region and the reverse bias region. In forward bias, we can connect the p-type semiconductor with the positive supply, and n-type semiconductor with the negative supply, and in reverse bias region, p-type semiconductor with the negative supply and n-type semiconductor with the positive supply. So here we can see if the zero bias case is there, then their net current will be zero, because due to the development of the barrier potential in the depletion region. This barrier potential stops the further movement of majority charge carriers across the junction. So in forward bias, we can say like p-type semiconductor is connected with the positive supply, and n-type semiconductor is connected with the negative supply. And due to the and we can see the barrier potential that is developed within the depletion region, it is from minus to plus. So due to this supply, this barrier potential will be eliminated due to this application of this voltage. And now the majority charge carriers from the p-type semiconductor, they will move towards the n-type, and the majority charge carriers in the n-type, that is the electrons, they move towards the p-type, and due to which majority current will be flowing. And this barrier potential, it will support the flow of the minority charge carrier. So majority charge carrier is from p to n, and minority charge carriers is from n to p. So net current in this case will be I majority minus I minority. And in forward bias, if we increase the forward bias voltage, then we can see the more number of majority charge carriers will cross the junction. That's why depletion layer width will be decreasing in this case, and it also offers the low resistance. The resistance is in the range of 10 ohms to 100 ohms for the practical diode, and for idle diode the resistance is 0. And in case of the reverse bias, we connect the p-type semiconductor with the negative supply and n-type semiconductor with the positive supply, and due to the application of this, we can see the barrier potentials are more strong due to the application of this voltage, and they stop the further movement of majority charge carriers across the junction. That's why the majority current is 0 in this case, and this barrier potential, they only supports the movement of the minority charge carrier. And here the minority charge carriers involve at all the places in the semiconductors, all the minority charge carriers will get involved in the conduction. So minority current will be more in here in comparison to the forward bias. So and this is the minority charge carriers are very less in number, that's why minority current will be very low, that is in the microampere. So if we increase the reverse bias voltage, then more number of minority charge carriers will be flowing across the junction, and at a certain point all the minority charge carriers within the semiconductor, they all get involved in the conduction, and that current is called the reverse saturation current. Now this current does not depend upon the reverse bias voltage. If we increase the reverse bias voltage, then this reverse saturation current will not increase. Only if we increase this, after a certain point breakdown will occur, means huge amount of current will flow and the diode will get damaged. So at this point the reverse saturation current depend only on the temperature. If we increase the temperature, then only the reverse saturation current will increase. So this is the VI characteristic of the PN junction diode, and this region is the forward bias and this region is the reverse bias. Here we can see this, these are the voltage. Here this is the current in the milliampere and this is the current in the microampere. So this is the reverse bias and this is the forward bias here. So we can see in forward bias the net current is given by the I majority minus I minority. So this current is the I majority, this is the I minority. So this IS in e to the power Vd upon eta Vt minus 1. IS is the reverse saturation current, Vd is the voltage drop across the diode, and eta is the this is the depends upon the type of material. Vt is the thermal voltage. Vt is given by Kt by Q. K is the Boltzmann constant. T is the temperature in Kelvin, and Q is the charge on the charge carriers. So if at room temperature, the value of Kt Vt is given by 26 millivolt, and this is the reverse saturation current. And reverse bias, the amount of current is given by minus Is, because we have to remove this part, majority charge carrier, and we will take only the minority charge carrier here, and that's why it will be minus Is here, and here it is the Id. Here the amount of current will be like in this way, eta Vd upon eta Vt minus 1. So this is the current that will be flowing in the forward bias, and minus Is the current that is flowing in the reverse bias region. So this is the net current diode equation, that is Id is equal to Is e to the power Vd eta Vt minus 1. Vt, like this is the diode, and we have applied supply across this diode, and due to this supply Vs, there is a voltage developed across this diode, that is called the Vd, and the current flowing through this diode is called the Id. So forward bias voltage, like our diode is this, and we have to do the forward bias it. So if it is a silicon diode, so minimum voltage that is required by this diode will be 0.7, because the barrier potential of the silicon diode is 0.7. So the cut-in voltage, the minimum voltage that is required for the diode to be in the conducting state, it will be 0.7 volt. So this slide shows the difference in between the VI characteristics of the germanium, silicon and gallium arsenide. So germanium, we know that cutting voltage of the germanium is 0.3, silicon 0.7, gallium arsenide 1.1 electrovolt. So means the germanium requires the less cut-in voltage. It will start earlier in comparison to silicon and germanium. And the reverse saturation current in case of the germanium is very high in comparison to silicon and germanium. The reverse saturation current for gallium arsenide is very less, and the breakdown voltage of the gallium arsenide is more in comparison to silicon and germanium. So what will be the effect of temperature on diode? So in the forward bias region, the characteristic of the silicon diode shifts to the left at a rate of 2.5 millivolt per centigrade degree increase in temperature. Means like this is the VI characteristics of the PN junction diode, and this starts conducting at 0.7. So if we increase the temperature, so this conduction will start early, and the characteristic will move towards the left side, like in this way. So the decreasing rate is the 2.5 millivolt per centigrade degree. And in the reverse bias region, the reverse saturation current of the silicon diode doubles for every 10 degree centigrade rise in temperature. This is the reverse saturation current, and then this current depends upon the temperature, and for every 10 degree centigrade rise, it becomes double. And thermal voltage, the formula of thermal voltage is given by KT by Q. This is the thermal voltage Vt. So it depends upon the temperature. So if we increase the temperature, thermal voltage will also get increased. The reverse breakdown voltage of a semiconductor diode will increase or decrease with temperature depending upon the Zener potential. Zener potential means at which the breakdown will occur. If it is between the 5 to 8 volt, then it will be the Zener breakdown. And if it is beyond the 8 volt, then it will be the avalanche breakdown. In case of the Zener breakdown, if we increase the temperature, then the breakdown voltage will get decreased. And in case of the avalanche breakdown, if we increase the temperature, breakdown voltage will increase. So that is why it is written here that reverse breakdown voltage of a semiconductor diode will increase or decrease with temperature depending on the Zener potential. So this is the breakdown mechanism. So there are two types of breakdown mechanism, that is Zener breakdown and avalanche breakdown. Zener breakdown, actually Zener diode is heavily doped, due to which the thickness of the depletion layer is very less. So here it is like this is the PN junction diode, and it is heavily doped, due to which the depletion layer thickness is very small. This is very small, and due to which the electric field intensity is very high. Intensity depends upon the area. So area is very small, so intensity is very high. So due to this high electric field in strength or intensity, the covalent bonds of the atom, it will get break, and the electrons become free. And electrons become free, and then the minority charge carriers will become free, and the current conduction will be there. So in case of the Zener breakdown occurs due to the heavily doping, and the thickness of the depletion layer is very small in case of the Zener breakdown. So reverse bias increases the electrical field across the depletion region, and this is with the avalanche breakdown. Avalanche breakdown occurs between the beyond the voltage 8 volt, and due to which this high voltage, the velocity of the charge carriers is very high, and they collide with the atoms, and after their collision, they impart their energy to the atoms, and the atoms liberates the another electrons, and this is a chain process. And also the avalanche breakdown occur, very low doping is there, due to which the electric field strength is not very high in case of the avalanche breakdown. So the process continues, and the electric field becomes so much higher, than the reverse current starts flowing in the PN junction. The process is known as the avalanche breakdown. After the breakdown, the junction cannot regain its original position because the diode is completely burnt off. The phenomenon of the Zener breakdown occurs in the very thin depletion region. The thin depletion region has more number of free electrons. The reverse bias applies across the PN junction, develops the electric field intensity across the depletion region. The strength of the electric field intensity becomes very high. The electric field intensity increases the kinetic energy of the free charge carriers, thereby carriers start jumping from one region to another. So the main difference between both are that Zener breakdown occurs due to the high electric field strength, and the avalanche breakdown occurs due to the very high velocity of the kinetic energy of the charge carriers. So this shows the VI characteristics of the Zener breakdown and the avalanche breakdown. So here we can see this Zener breakdown occurs at the voltage between 5 to 8 volt, and this avalanche occurs beyond to 7 volt. And this characteristic has a sharp curve, and it does not have a sharp curve here. It occurs at heavily doping, and it occurs at low doping. So this slide depicts the difference between the Zener breakdown and avalanche breakdown. So this is observed in Zener breakdown. This is observed in Zener diodes having VZ 5 to 8 volt. This is observed in Zener diode having VZ greater than 8 volt. And second point, the valence electrons are pulled into the conduction band due to very intense electric field appearing across the narrow depletion region. And in avalanche breakdown, the valence electrons are pushed into the conduction band due to the energy imparted by colliding accelerated minority carriers. It occurs in heavily doped diode. And avalanche breakdown, it occurs in normally doped diode. The breakdown voltage decreases with increase in temperature, and the breakdown voltage increases with increase in temperature. So these are the differences, main differences between the Zener and the avalanche breakdown. So diode equivalent circuits. So this is the circuits, how we can express the, we have a circuit in which the diode is there, resistances are there, and supplies are there. So we can, we have to draw the mathematical model of the diode. So we can use three models: piecewise linear model, simplified model, ideal approximation for the analysis of the circuit. So in piecewise linear model, like this is the VI characteristics of the PN junction diode. So we have taken the linear model of the characteristic. We have drawn the segment from here, and in generally this model is used when the resistance is connected in the circuit with a diode. These resistances are of the range of the resistance of the diode. Like diode has a resistance of 10 ohm, and the other resistances are connected in the circuits are also in the range of 10 ohm, like 8 ohm, 11 ohm nearby. So we cannot ignore the resistance of the diode in that case. And also the supplies that is connected across the diode, like this is the supply that is connected across this diode, it is equivalent to 0.7, nearby 0.7, like it is 1 volt, 1.7 volt. So we cannot neglect the barrier potential or the cut-in voltage required by the diode. So this model is very rarely used. Simplified model, this model is generally used for the numerical problems, and in that case this is our diode and it is connected with the circuit, like resistances are there and supplies are there, like in this way. So like the resistance of the diode is RAB, and that is the 10 ohm, and here the resistances are 2K, 3K. So these are the R network. This R network is very high in comparison to the 10 ohm. So we can ignore the resistance of the diode, and the supply that is connected here are in the range of 1 volt, 2 volt, 3 volt. So we cannot ignore the cut-in voltage of the diode. So here the characteristics, VI characteristics, like was in this way, but this resistance has become zero. So this slant line has become a straight vertical line. This is the line, and this shows the resistance of the diode 0 here. So this model is generally preferred and preferably used for the numerical problems. Ideal approximation means the diode is our ideal. Here the R network is very high in comparison to resistance of the diode, and also E network is very high in comparison to the cut-in voltage of the diode. So here we can see now the cut-in voltage has become 0. So now this is the operating area of the diode. So in first case the characteristic was like in this way. In second case, it has become like in this way, and in third case, it has become like in this way. So these are the three models that we can use for the analysis purpose. Here we can see this is like in this is a slant line, this is a straight vertical line, and this is the line that had the origin 0. Here ideal device, that is R network is greater than RAB. Here E network is greater than VK. Here R network is greater than RAB. So this is the numerical that can be solved by using the simplified model. So here practical diode is given, that is SI, and SI is written here. So this SI will be replaced with the 0.7 volt. So here it will be 0.7, here it will be 0.7. So we have to find the value V0. V0 is a voltage across at this point. I1, ID1 and ID2. We have to find out this. So we can see these both diodes are connected in parallel. So the value of ID1 and ID2 will be same. And the voltage across this ID1 and SI diodes, D1 and D2, it will be equal to V0. So we can find, and this V0 would be equal to 0.7 because this diode will be short and it will be replaced with the 0.7 volt. So this will be 0.7, and this is also 0.7. So now we can apply KVL here. So after applying KVL, we can see 10 volt minus 0.7 upon 0.33, and the I1 will be 28.18 milliampere, and this ID1 is equal to ID2, that is equal to I1 divided by 2. So it will be 28.18 milliampere divided by 2, 14.09 milliampere. So this is how we can find the value of V0, I1, ID2. I1, how can we find the value of I1? By simply, we can find this 10 volt minus 0.7. So we can find the value of VR. 10 minus 0.7, we can find the value of VR. Now we can divide the value by 0.33. So it will be 28.18 milliampere. So now this is the second numerical, and we can see here, this is the silicon diode is there, and this is also the silicon diode is there. So we can draw the equivalent model of this numerical question. So here we can replace this silicon Si with the 0.7 volt. We can replace this Si with the 0.7, and it can also be replaced with the 0.7. And then we can apply KVL here, and we have to find the I1, value of I1. So I1 is this much. I2, the value of I2 is this much. And then ID2 is this much. So we have to find all these values. So I1 we can find out. For finding the I1, we have used 0.7 VK2. Like this is the because this 0.7, the voltage across this resistance, it will also be 0.7. So 0.7 divided by 3.3, that will be 0.212. This will be the I1. And now we can find the value of I2. For finding the value of I2, we will have to find the value of V2, the voltage across this part. So we have applied KVL here, and we have found the value of V2, that is 18.6 here. And for I2, it will be V2 divided by R2. It will be 3.32 milliampere. And now ID2 is the current here. So this current will be I1 minus I2. Or we can say this is the current. This is the I2 is the current. This current is divided into ID2 and I1. So ID2 will be I2 minus I1. So we can find the value of ID2 by subtracting I1 from the I2. So this value is the 3.11 milliampere. So in this way, we have seen in this lecture, we have seen the working of the PN junction diode. How can we use a PN junction diode in forward bias, in reverse bias, and in zero bias. In case of zero bias, there will be a no current will be there, and only the formation of depletion layer will be there. And in forward bias, the net current will be I majority minus I minority. And in reverse bias, it will be only the minority current that will be flowing. And the differences between the practical diode and the ideal diodes are like practical diode, their VI characteristics are like in this way. This is a VI characteristic of practical diode. This is V and this is the I. And for the ideal diode, this characteristic is like in this way. This is the straight line. So all the characteristics of practical and ideal diode we will discuss in the next lecture. Thank you.